Hello, and welcome to Lesson 7 of this Introduction to Linear Algebra with Wolfram U. The topic of the lesson is linear transformations. So let's begin with a brief overview of the lesson. So let's say you look over here at this matrix equation Ax equal to b. That's the matrix A. It's got the first row 2, 1, the second row 3, 4, and that's the vector x, 1 and 2, and that's the right hand side b, 4, 11. Now, this equation over here may be regarded as a transformation which takes the vector x on the left hand side and transform into vector b on the right hand side. Now, you may recall that the dot product of a matrix satisfies a couple of properties, namely that a dot u plus v is a dot u plus a dot v, and a dot cu is c times a dot u. So those two are the important properties of dot product. And so this over here is an example of what we would call a linear transformation. And that's the topic of this lesson. Now, these linear transformations actually provide the foundations for many important topics that occur later on in linear algebra. Okay, so let's begin a little simpler and first of all talk about the idea of a transformation. So a transformation from one Rn to another Rm, let's say, is a rule which assigns to each vector in the first Rn x another vector t of x in Rm. And the first set is called the domain. The second one is called the codomain. And if you take a vector x in Rn, then the vector t of x is called the image of x for reasons which we'll just see in a few moments. And the set of all these images is called the range of t. So roughly speaking, that's the set of vectors in Rm which actually get used by t. Okay, so as an example, here's a transformation. It takes a point a comma b and transfer to the point a comma negative b. So for example, if it has 2 comma 3 as the input, then you get back 2 comma negative 3 as the output. Now in this case, of course, the codomain and the domain are both R2, and the image of AB is a comma negative b. So this is a reflection in the x-axis. So let's see that over here. You have the point 2 comma 3, and after transformation you get the point 2 comma negative 3. That's a reflection if you imagine a mirror placed in the x-axis. And of course the range of this transformation is all of R2 because every point over here comes from some point under the reflection. Okay, so now let's talk about linear transformations. So transformation is linear if it satisfies the two properties t of u plus v, t is tu plus tv, and t times cu is c times tu for all scalars and vectors. Now, it turns out that if t is a linear transformation, then you get two properties kind of free of charge. You can say that t of 0 is 0. That works out automatically. And if you do a kind of linear combination over here, then the image under t is c times tu plus d times tv. So that's a linear transformation. It's a very special kind of transformation. And as an example of linear transformation, here is the transformation t, which is given by t of xy equal to 2x comma 2y. So that's a kind of dilation. It expands vectors, dilates them. So if you take 3 comma 4 as the input, then the output is 6 comma 8. So here's a plot. That's the original vector 3 comma 4. That's the kind of image 6 comma 8, and you can see it's a dilation from the origin with center the origin. Okay, so the question is, why is this a linear transformation? So let's put down the definition again and try and see why it is linear. So here are two vectors u and v. U is u1, u2, v is v1, v2. Let's check that if you do t of u plus v, you get back the same as tu plus tv. So first do t of u plus v. That looks a bit undersimplified, so we expand it. And now if you compare with t of u plus t of v, you get back exactly the same result. And then you check the second property. So if we do T of C times U, that's the same as C times T of U. So what we've done over here is to prove that this dilation is actually a linear transformation. So dilations are a simple example of linear transformations. Okay, so having talked about that, let's go on to a very important class of transformations, which are matrix transformations. So if you have a matrix A, then it defines a transformation T. And that transformation simply does A dot x or A times x for every vector x. And often you'll see in books or elsewhere the notation x goes to A of x for such a transformation. Now, these matrix transformations automatically satisfy the linear transformation definition because A dot u plus v is A dot u plus A dot v, and A dot cu is C times A dot u. So the point over here is that every matrix transformation is actually a linear transformation. So every time you have a matrix, you actually have a linear transformation. And the question is, what's the range? Well, the range in this case is all linear combinations of the columns of A. After all, when you do A dot x, you're taking linear combinations of the columns of A using the vector x. Okay, so as an example of a matrix transformation, here's a matrix A, and that's a matrix form. It's got 3 rows and 2 columns. So you take a 2 vector 3, 4, compute its image. You simply do A dot u, and of course you get back a 3 vector because there are 3 entries over here. Okay, so next take a vector B and ask the question, does this vector B belong to the range of A or not? So to understand that, you do linear solve of A comma B and you get back an answer, and you see over here that that answer V dotted with A does give you back B. So B is certainly in the range of A. The vector over here is in the range of A. But if you take the vector C over here and you try and do the same thing, you see over here that this vector does not belong to the range, and you get back a message saying that this linear equation has no solution. So every matrix will define a linear transformation for you. And a second example here is a matrix, very simple matrix. It's got entries 1, 0 and 0, -1. So let's see what happens if you try and find the images of a few vectors under this transformation. So let's take 3 vectors u, v and w. U is 5, 0. If you apply A to it, you get back 5, 0, just get back the same vector. If you apply 0, 5, you get back 0, -5. If you apply 2, 3, you get back 2, -3. So that should remind you of the first example in the lesson. And let's see what happens if you do a kind of plot over here. And you see over here that in fact, every point is reflected in the x-axis under this transformation, and hence this is a reflection. So this simple matrix over here actually defines a reflection in the x-axis. So what you've shown now is that you can define a reflection using a matrix. Okay, so that brings me to the end of the lesson, and there are just 3 points to take away from here. The first point is that there is a close connection between linear transformations and matrices. In fact, every time you get a matrix, so every matrix will define for you a linear transformation. But the question is, how about the converse? Well, if you have a linear transformation, then can you define its matrix or not? And that's the topic of the next lesson, which will be about the matrix of a linear transformation. So I'll stop over here. This is a very important concept, the relation between linear transformation matrices. Do review it before we start the next lesson. Thank you very much. I'll stop over here.